Welcome to a new edition of Tales of the Workshop. Today we're going to feature forward and reversing circuits as featured in garage door openers. So follow me into the shop and let's get this thing started. So here we've got a set of Allen Bradley forward reversing contactors. Now this is a catalog item. They can be purchased. This particular setup was meant for a three-phase induction motor. Now we've got forward reversing as well as we've got a single overload relay. Why one overload relay is because of the fact we're only dealing with one motor. It is going either in forward or reverse and only requires the one overload relay. Things that are unique to this type of setup when you purchase it from the manufacturer, according to standards, contactors are supposed to be mechanically interlocked. Now what that means is that if I was to force the contacts, now if we can see in the window right here, if I force the contacts closed on this armature, and it should show open here, and if I was to try and force the contacts over here, the mechanical interlock would prevent this second armature from closing. So if I'm actually trying to push it, it's not going to happen. So that's why we have mechanical interlock. We do not want to see two contactor coils energized at the same time, due to the fact it would cause a phase-to-phase short, and that's something we really want to avoid. Now we're going to get a close-up so we can see this a little bit more in detail. As well, I want to be able to show my viewers that the wiring right here, or there's a set of jumpers that come to us directly from the factory. When I take one of these out of the box, my primary concern is just wiring up the input, so my feed, as well as the output going out to the motor, and then my control circuit. Now you can see that some of this has already been wired from the factory. So we already got electrical interlocks. All we have to do is wire up to the coils and we can complete our circuit. But we're going to get a little close up and we're going to have a look at these jumpers. In order to illustrate this a little bit better, I've decided I'm going to withdraw these covers so we can actually see the armature and the contacts. So bear with me here. We're going to remove the cover plate and we'll remove this one. So we want to see the mechanical interlock in action. So now we can see the armatures as well as the bridge contacts of both of my contactors. Now you can see that there's a window right here as well as right here. So that gives us a visual indication of the state of the contactor, letting us know which of the contactors is energized at any one point in time. Now, I am going to be able to manually close the armature, and when I do this, pay attention to the window. You can see it goes from an off to an on. Now, with the mechanical interlock, so that's what's going on in behind here. If I was to do the same thing with this armature, but you can see I'm trying to push down, and the contacts, the bridge contacts, and the armature will physically not move. Now, I have to release this armature. The bridge contacts have opened. Now I'm going to close the opposing contactor's armature. We can see that the bridge contacts have changed state. The window has now went from an off to an on. And if I try and close these contacts over here, you can see there's a little bit of movement, but the mechanical interlock is preventing this armature from being drawn in. So this is the reason why no one contactor can be energized at any one point in time, because we have a mechanical interlock that the manufacturer has built into this assembly. But in the electrical field, we don't just depend on the one the one interlock, we're going to follow it up with an electrical interlock. So we call that redundancy. Now there's two forms of electrical interlock. One of them is right here, that we have normally closed contacts. Now I'm pretty sure the camera can see this, but we can see the icon of a normally closed contact here as well as here. And when we go through the schematic diagram, I'm going to highlight that. Here, terminals 5 and 4 relate to this contactor, and these are the holding contacts for this contactor. Terminals 2 and 3 are the holding contacts for this contactor. You also may notice that this is all wired in red, and this comes to us directly from the manufacturer. All we have to be worried about as electrical workers is to bring in the incoming power to the top of one of these contactors. Which one is irrelevant, because we actually have bridges that have been pre-wired, supplied to us from the manufacturer. And I'm going to reset things, and I'll be right back, and we're going to look at these jumpers in detail. I've gone ahead and I have removed on this contactor with the goal of allowing my viewers to see how the bridge contacts are in a linear relationship. That this is an L1, this is considered to be T1, which is the output. L2, T2, L3, T3. The same applies to the opposing contactor. Now when we talk about the jumpers, because this is the input, or the L, jumpers are already in place from the manufacturer, and that the L1 of this contactor is connected to the L1 of the opposing contactor. The same applies for L2 to L2, L3 to L3. Now, if I turn this around, maybe we can get a better view of it. So let's see, can we see it a little bit better? What we can see is that this tab comes across, so L3 going to L3, L2 to L2, and that's kind of hidden behind here. But now, let's turn this back around and examine the output. Now, we mentioned previously that it was an accepted industry standard that when we are switching the direction of rotation of a three-phase induction motor, it's standard practice to switch out the A or red phase for the blue phase. And that is what is mirrored here. This is T1. So L1, T1. T1 should be connected to T3 of the opposing contactor. So if I was to follow this little metal strip, I don't know if the camera can pick that up, but if you follow it all the way across, it hooks up to T3 of the opposing contactor. What we can see is that the T3 of this contactor is connected to T1 of this contactor. Now, T2, there's no change, because we only need 2 phases to change direction of rotation of a 3-phase induction motor. Also, as an added little feature, I can actually force the armature, so we can actually see the bridge contacts opening and closing. So we can actually see. Now, this is a size 1 contactor, and the size 1 contactor is based off of the current carrying ability of these contacts. So when we talk about current carrying abilities, there's 2 things that come to mind: the surface area of the contacts, as well as the air gap in between these contacts. That's one of the reasons, or the primary reasons, why contactors uses primarily bridge contacts. They break at 2 places, and the reason why we want 2 air gaps is that they become additive, and we have the ability to switch progressively higher amounts of current without the fear of arcing going across from the contacts themselves. And so it is an issue of safety. Now, let's go and have a look at the actual schematic diagram and how this is designed to function.
So here we have an atypical forward reversing circuit, and we're going to discuss some of the things or elaborate based off of what we saw in the workshop, namely the construction of the contactor, the mechanical interlock, and we alluded to the introduction of electrical interlock. Now, I'm going to take a moment here and I'm going to trace out what this circuit would look like in its at-rest state with the circuit energized. Here we are. Now, for the sake of simplicity, what I've gone ahead and done is I've color-coded the lines coming in from the power supply. Consistent with Canadian code, L1 is denoted and identified as red, L2 as black, and L3 as blue. I thought it would be really good for people to get a better sense of what is going on if we color-coded things. Now, a few things before we get started. Please note that there's a dashed line right down here between the forward and reversing contactor coils. And we do see a note that says mechanical interlock. The dashed outlines on diagrams between components usually indicates that there's a physical relationship between the contactors. In this case in particular, that there is a mechanical interlock. We have put a dot or a dashed line for the sake of elaboration or for teaching to show people that these contacts constitute what is known as an electrical interlock. And we're going to delve into this a little bit more in detail. Now, I'm going to grab an annotation tool and we're going to narrate the process of what is going to happen when we depress the forward push button. Now, I'm using the analogy of a garage door. So the forward push button, in reality, I'm going to call it up. So when I depress my forward push button or my up push button, what am I doing? I'm basically establishing momentarily a path for control power to flow through this rung in the circuit. Now, the electrical interlock, we actually have the R maintained contact or normally closed contact, and control power is going to flow through that contact and is going to allow the up or forward contactor coil to energize. Now that coil is in series with the overload normally closed contact, and it's going to flow through that contact, and it's going to complete the circuit by going back to X2 of the control transformer. We have an auxiliary contact. That auxiliary contact for the up contactor is going to change state. So then I can release my finger off of the up or forward push button. I'm going to grab a little eraser and we're going to erase that. Now that's established that the control circuit has pulled in. Up in the power circuit, we're going to use red. The F bridge contacts do change state. L1 or the red phase is going to flow through and is going to go to the windings. I got to change colors. The black phase going to flow through, and the blue phase is going to have complete voltage and current flowing through it, allowing us to complete that circuit. And for the sake of argument, we're going to say that the motor is turning in the clockwise direction and everything's good. Now, if someone was to come along and try and depress the reverse push button, so I'm going to put an arrow right here. Well, bear in mind that in this rung, when the contactor coil or the up contactor coil changed state, then this F, normally closed contact, opened. If someone was to depress the reverse push button, nothing would happen because that rung is now incapacitated and is incomplete. In order to be able to access the reverse function or the down function, as the case may be, it's going to require us to go ahead and hit the stop push button. Now, if I do that, I'm going to grab an eraser. We're going to hit the stop push button. Once I've done this, what have I done is I've interrupted the flow of control power in this run. The up or the F contactor coil is going to drop out. When that happens, well, now this whole part of the rung is going to de-energize because the F auxiliary contact has lost power. Up above, the F bridge contacts now open and is interrupted the flow of line voltage flowing to the motor. When that happens, the motor loses power and is going to come to a stop. Once the motor has come to a stop, I can then go ahead. So the stop push button, these are maintained contacts. So once I release the stop push button, everything would have reset itself. And now I have the ability of depressing the reverse push button. Once I do that, we're going to pretend like I've hit the reverse push button. So I'm going to momentarily bridge that set of momentary contacts, allowing for control power to flow through, remembering that the normally closed contacts of the F coil have now reverted back to their shelf state, allowing for this to happen. I'm going to have power flowing through to the R or the reversing coil, or in the case of the garage door, the down contactor. And it'll complete the circuit just as the F contactor did before. Now, the auxiliary contacts are going to change state, sealing that part of the circuit. Up above, the R bridge contacts change state, establishing a new path for line voltage to flow. Now we got to change colors. So red, well, now the red phase is going to flow, but it is now going to cross over into the blue phase, or the original, and is now going to establish a different direction of travel. Change colors again. Now, black, well, black does not change. It's actually, if we take a good look at it, the L2 or the black phase stays the same, and is the blue phase that switches with the red phase. So if we take a look, it's connected up into the red phase. And now, because we have changed or swapped two phases, what's going to happen is the motor is now going to turn in the counterclockwise rotation. Again, if someone was to come along and try and hit the forward push button, this contact, because the R or the down contactor is in operation, that contact is in the open state, it will not function. We must stop or depress the stop push button in order to shut down the circuit. This is good, but there's some room for improvement here. The fact, if we have to depress the stop push button each and every time we want to go from forward to reverse, could be seen as a bit of a nuisance. And looking at design, we want to maybe make some subtle improvements. And there are areas in which we can make these improvements. And what we're going to do is we're going to go and look at a different diagram. So here we are at our second diagram. It is the same basic diagram. The only change is the inclusion of push button interlocks. Now, what's the main advantage of putting in a second set of electrical interlocks? I had mentioned previously that there was some room for improvement. This circuit allows us to switch from the forward directional rotation to the reverse directional rotation without having to hit the stop button. And we're going to look at this in particular. If we look at the power circuit, there has been no changes whatsoever. When we look at the relationship of the contactors, No changes whatsoever. The same thing would apply with the electrical interlocks. There's no changes here. Now, I want to bring to your attention right here that this is different from what you've probably seen previously. There's some dashed lines in between the forward and the reverse. If we look at this note over here, the dashed lines represent that there's a physical relationship between these push buttons. Now, in reality, it's the same push button, or we would call it the same operator. When we would look at the control station, I would still see only 3 push buttons: the stop, the forward, and the reverse. But electrically, inside of the control station, I've actually got 2 contact blocks. And that's why we have this physical relationship to show people, whoever's reading the diagram, that there's 2 contact blocks, and each of those contact blocks is wired in a different rung in the circuit. Now, I'm going to go off camera for a second, and I'm going to highlight different parts of this, and we're going to take you through it. Now, in the interest of time, I've enlarged the diagram to make it a little bit easier to see. And for the forward direction, I'm going to use a different color just so we can differentiate. Now, in this case here, if an operator was going to go ahead and hit the forward direction, they're going to momentarily depress the forward push button, like so. And that's going to establish a path for control power to flow through the maintained contacts of the reverse push button. Remember, that's a second contact block. That is going to allow us to flow power through the electrical interlock of the normally closed R auxiliary contact. And then that's going to allow us to energize the forward contactor, establishing a path through the normally closed contacts of the overload relay. And that's going to continue in its path to X2 of the control transformer. And so this coil is energized. We've also got the auxiliary contacts down here that are going to change state, that's going to seal the circuit, at which point we can take our finger off the forward push button and the motor is going to be operating in the forward direction. In this case here, if an individual was to go ahead and hit the reverse push button right here, they're going to unleash a sequence of events. And I'm going to grab my eraser. We'll talk about that. So by depressing the forward push button, inadvertently, because there is this physical relationship between the terminals, the terminal block 3 and 4 and terminals 1 and 2 of the reverse push button, by depressing the push button, you're going to open up the maintained contacts. Once that happens, control power has now been interrupted to this rung. When that happens, the coil of the forward contactor loses power. This drops out. This whole line now loses control power, and then the F auxiliary contact opens up. The motor now is disconnected from the line and can now potentially be brought back online, but in the reverse direction. Now, all of this is happening in a fraction of a second. Now, I'm going to grab a different color, and we're going to highlight in the opposing direction of operation here. So we depress, so someone went ahead and depressed the reverse push button. When they did that, they opened up this contact. This contact, once the F contactor coil de-energized, the F normally closed contact reverted back to its shelf state. So we actually have a continuous path. The F maintained contact is closed. This is reverted back to its shelf state. So we can allow for control power to flow through to terminal 17, flow through the contactor coil, and it's going to complete the circuit going through, again, the same set of normally closed contacts of the overload relay. And this is now energized. Down here, the small branch in the R auxiliary contact changes state, sealing the circuit, and we can take our finger off of the reverse push button. And this is going to operate in the opposing direction for as long as we dictate it to. And that's how it's supposed to function. The only problem I see with this circuit, though, is it still relies on the operator to know when to turn the circuit off. And we don't have any type of automation. Bear in mind that we're using a garage door as an example. There's still a little bit more work that needs to happen here in order to have a fully automated circuit. Because I know that when I hit the up function on my garage door, I don't have to go back and make it stop. It stops on its own. That means then that we need a couple other devices to be added to this circuit to give us that automatic function I was speaking of.
Now that we've looked at the basic circuit of how a garage door is supposed to function, one of the important things we have to start looking at is what system is in place to help limit the travel of the door. Now, when we look at the track, we can see that the door is in a fully open position, and we see that there's a stud here that's going to limit the travel. But don't we need something in place to stop the circuit? Otherwise, the door is going to go and force up against that stud and possibly damage the motor. The same thing is going to apply when the door hits the bottom. What limits the travel of the door, and how does the system know when the door is in a fully closed position and it's going to turn off the system? What we have to do is think about these things. Now, the solution lies in limit switches. Now, limit switches are designed to limit the travel distance of a door or even an elevator or an overhead crane or hoist. What it's designed to do is when the door has hit its maximum area of travel, and in our case, I want to make sure that my door is in the fully open position. So when the door hits the top, I need it to turn off. And that's where a limit switch is going to come in. Now, regardless if we're talking about a three-phase system or a single-phase system, the principles remain the same. We require something that's going to limit the travel distance of the door.
So here we have the same basic circuit, but now we've incorporated travel limits. You'll notice that everything above the blue line up here remains unchanged. What we've done is we've added some shaded boxes because I wanted to take an opportunity to mention that everything in the control station that is readily available to the operator is located here in the circuit. And then the remaining components find themselves inside of the enclosure. Notice that the limits find themselves inside of the enclosure. Now, designing a circuit, what we never want to see is that upper limits are placed in between the stop and forward or reverse push buttons. We should also never see them over here ahead of the control station. It's just not done. What we want to do is limit the number of conductors that are going from the enclosure down to the push button station. And then all the other components come into the enclosure themselves. Now, what I'm going to do is I'd like to expand or enlarge this diagram because all of the changes we're talking about are relevant to the control circuit. As I said earlier, there has been no changes to the power circuit. And so now that we're back, let's have a look at how things are supposed to function in conjunction with an upper limit. An operator or an individual goes ahead and depresses his forward push button, meaning he wants his garage door to go upwards. He wants to open things. He's establishing a temporary path because these are momentary contacts for control power to flow through the maintained contacts of the double or the push button interlock, namely the reverse push button. It's going to flow through the closed contacts because the upper limit is in a closed position, and through the electrical interlock of the opposing contactor, namely the R auxiliary contact, and finally the coil will be energized and it will complete that circuit by going through the normally closed contacts of the overload relay. I'm going to highlight that. So this is considered to be energized. We're also going to draw in that I want to take my finger off the forward push button or the up push button, and that the F auxiliary contacts will change state, sealing the circuit, allowing me to take my finger off the forward push button. And so the garage door is now going up. But once the garage door is in the fully open position, that is where the upper travel limit comes into play. We want to eliminate the possibility of human error. And if we did not have some process of automation in this system, we would constantly have to sit and monitor the garage door to make sure that once it was fully open, that we stopped the circuit. If it was fully closed, that we turned the circuit off. Otherwise, the door or the motor would continuously keep trying to turn to keep pushing the door downwards and eventually burn out the motor. In the case of an upper limit, if we didn't have an upper limit, chances are that the door would actually fall out of the track or possibly damage the garage door opening unit, which is something you want to avoid. And in this case, once the upper limit opens, what it does is it's dropping out the control power for the coil of the forward contactor. That means then that this rung loses power, the contacts lose power, and then this all drops out because the auxiliary contact will have opened. Now, the push buttons, as we saw in the previous diagram, remain unchanged. I could go ahead and go from the forward to the reverse direction of rotation without having to hit the stop button. So that part of the circuit remains unchanged. So I still got a lot more functionality, but now I have the ability turning or pushing the forward or the up push button and not have to mind the door. I can go about my business. The same thing would apply with the reverse function. I want to be able to just hit the down push button and then leave the garage confident in the knowledge that the system would turn itself off. And these are the kinds of things that we have to take into consideration.